Welcome back. So today I'm going to discuss on cubic splines. In the last episode we were discussing on Bezier curves. So let's see what is a cubic spline is. So given a set of control points, cubic interpolation splines are obtained by fitting the input points with a piecewise cubic polynomial curve that passes through every control point. So suppose if we have n plus 1 control points specified with coordinates p equal to xk, yk, zk, where k is equal to 0, 1, 2, etc. up to n control points. So this is the curve which shows the cubic spline. Okay. Now, we can describe the parametric cubic polynomial that is to be fitted between each pair of control points with the following set of equations. That is x of u equal to ax u3, ax u cube plus bx u square plus cx u plus dx, and y of u equal to ay u cube, by u square plus cy u plus dy, and z of u equal to az u cube plus bz u square plus cz u plus dz. So for each of these three equations, we need to determine the values of the four coefficients a, b, c and d in the polynomial representation for each of the n curve section between the n plus 1 control points. So we do this by setting enough boundary conditions at the joints between curve sections so that we can obtain numerical values for all the coefficient represented here. Now we have natural cubic spline. One of the first spline curves to be developed for graphics applications is the natural cubic spline. So we formulate a natural cubic spline by requiring that two adjacent curve sections have the same first and second parametric derivatives at their common boundary. Thus natural cubic spline have c raised to 2, that is c square continuity. This is represented as if we have n plus 1 control points to fit, then we have n curve sections with a total number of 4n polynomial coefficients to be determined. That means we have n plus 1 control points to fit, right? So we already said that if it is cubic spline or if it is a cubic curve, that is if it is the curve has 3 n's, then the control points will be n plus 1. So then we have an n curve sections with total of 4n polynomial coefficients to be determined. At each of the n minus 1 interior control points, we have 4 boundary conditions. So the two curve sections on either side of a control point must have the same first and second parametric derivatives at that control point, and each must pass through that control points. So thus this gives us 4n minus 4 equations to be satisfied by the 4n polynomial coefficients. We get an additional equation from the first control point P0, the position of the beginning of the curve, and another condition from control point Pn, which means be the last point on the curve. One method for obtaining the two additional conditions is to set the second derivatives at P0 and Pn to 0. So whatever conditions we have acquired by P0 and Pn, we have to set the second derivatives of both these points to 0. Another approach is to add extra dummy control points, one at each end of the original control point sequence. We are adding extra dummy control points. So that is, we add a control point P minus 1 and a control point Pn plus 1. Then all the original control points are interior points and we have necessary 4n boundary conditions. Our next topic is visible surface detection methods. So a major consideration in the generation of realistic graphic display is identifying those parts of a scene that are visible from a chosen viewing position. So how the viewers view to choose a scene. That is the major graphics display, realistic graphic display to be identified. So here numerous algorithms have been devised for efficient identification of visible objects for different types of applications. So these algorithms are referred to as visible surface detection methods or hidden surface elimination methods. Basically, we call it as visible surface detection methods because in wireframe model, you have seen that only the visible part has been wireframed, right? And that is known as the visible surface detection. So there is a classification for visible surface detection method. That is, visible surface detection algorithms are broadly classified according to whether they deal with object definitions directly or with their projected images. So there are two methods, that is object space method and image space method. We'll see first what is object space method. So object space methods compares objects and parts of objects to each other within the scene definition to determine which surfaces as a whole we should label as visible. So in object space method, the objects and parts of the objects are being compared with each other, and we will determine or we will label which is the visible part. On the other hand, in an image space algorithm, visibility is decided point by point at each pixel position on the projection plane. So we'll choose a projection plane and we will decide the visibility point by point. So first visible surface detection method is the backface detection. A fast and simple object space method for identifying the backspaces of a polyhedron is based on the inside-outside tests. Let's see what are the inside-outside tests. A point XYZ is inside a polygon surface with plane parameters A, B, C and D if AX plus BY plus CZ plus D is less than 0. Okay. When an inside point is along the line of sight to the surface, the polygon must be a backface. So if we say that an inside point is along the line of sight to the surface, we determine that the polygon must be a backface. Okay. So which means that we are inside that face and cannot see the front of it. Which means that we are inside the face and we cannot view the front of the polygon. Okay. From our viewing position, we cannot see the front of the polygon. Now we can simplify this test by considering the normal vector n to a polygon surface which has Cartesian components a, b, c. In general, if v is a vector in the viewing direction from the eye or camera position, then this polygon is a backface if v into n or v dot n greater than 0. Okay, now vector, this is a figure showing vector v in the viewing direction. You can see v view in the viewing direction and a backface normal vector capital N of a polyhedron. Okay. Now if object descriptions have been converted to project coordinates and our viewing direction is parallel to the viewing z axis, then v is equal to 0, 0 vz and v dot n is equal to vzc. Okay. In a right-handed viewing system with viewing direction along the negative ZV axis, the polygon is a backface if C is less than 0. Also, we cannot see any face whose normal has Z component. That means C is equal to 0 since our viewing direction is grazing that polygon. Okay, thus in general, we can label any polygon as a backface if its normal vector has a Z component value C greater than or equal to 0. So we are representing C as the Z component value. Let's see a figure based on this. See, this is a polygon surface with the plane parameter C less than 0 in the right-handed viewing coordinate system. Is identified as a backface when the viewing direction is along the negative ZV axis. Viewing direction is along the negative ZV axis. So we can see that the Z component is less than 0 when it is in the negative ZV axis. Okay. Now we have the next method or invisible surface detection, that is the depth buffer method. So a commonly used image space approach to detecting visible surfaces is the depth buffer method, which compares surface depth at each pixel position on the projection plane. This procedure is also referred to as the Z buffer method since object depth is usually measured from the view plane along the Z axis of a viewing system. Okay, so we are viewing the system along the Z axis. Okay, that is why it is known as Z buffer method. Okay, each surface of a scene is processed separately, one point at a time across the surface. So the method is usually applied to scenes containing only polygon surfaces, because depth values can be computed very quickly when it is a polygon surface, and also the method is easy to implement. So with object descriptions converted to projection coordinates, each XYZ position on a polygon surface corresponds to the orthographic projection point XY on the view plane. It is only XY on the view plane because we are viewing through the Z axis. Therefore, for each pixel position X, Y on the view plane, object depths can be compared by comparing the Z values. So this is a figure which shows three surfaces at varying distances S1, S2, S3 along the orthographic position line from position X, Y on a view plane taken as the X, Y plane. Okay, so here the surface S1 is closest at this position. So its surface intensity value at X, Y is saved and kept. Okay. Now, as implied by the name of this method, two buffer areas are required here. A depth buffer is used to store depth values for each X, Y position as surfaces are processed, and a refresh buffer stores the intensity values for each position. Initially, all positions in the depth buffer are set to 0, that is the minimum depth, and the refresh buffer is initialized to the background intensity. Now, each surface listed in the polygon tables is then processed one scan line at a time, calculating the depth, that is the Z value at each XY pixel position. So here we have to draw scan lines. With these scan lines only, we are processing the polygon tables. Now the calculated depth is compared to the value previously stored in the depth buffer at that position. If the calculated depth is greater than the value stored in the depth buffer, the new depth value is stored and the surface intensity at that position is determined and placed in the same XY location in the refresh buffer. Now we'll see the algorithm. The first step is to initialize the depth buffer and refresh buffer, so that for all buffer positions X, Y, depth of X, Y equal to 0 and refresh of X, Y is equal to intensity of the background. Okay. Now for each position on each polygon surface, compare depth values to previously stored values in the depth buffer to determine its visibility. Now calculate the depth T for each XY position on the polygon. If Z is greater than depth of X, Y, then set depth of X, Y equal to 0 and refresh of X, Y equal to intensity surface of X, Y. So where I background is the value for the background intensity and I surface of X, Y is the projected intensity value of the surface at pixel positions X, Y. Now here, after all surfaces have been processed, the depth buffer contains depth values for the visible surfaces and the refresh buffer contains the corresponding intensity values for those surfaces. The depth values for a surface position X, Y are calculated from the plane equation for each surface, that is Z is equal to minus AX minus BY minus D divided by C. For any scan line, adjacent horizontal positions across the line differ by 1 and a vertical Y value on an adjacent scan line differs by 1. So if the depth of position XY has been determined to be Z, then the depth Z dash of the next position X plus 1, Y along the scan line is obtained as Z dash is equal to minus of A of X plus 1 minus BY minus D is equal to 0, which means Z dash is equal to Z minus A by C. So this is the positions which represent that if A has the position X, Y, then B will be having the position X plus 1, 5 on a scan line. Okay. Now on each scan line, we start by calculating the depth of a left edge of the polygon that intersects the scan line, right? So depth value at each successive position across the scan line are then calculated using the same equation Z dash is equal to Z minus A by C. So I hope today's episode was understandable and thank you so much.